April 25, 1986, 11 p.m., Chernobyl nuclear power plant, Ukraine. Reactor 4, Shift Supervisor Alexander Akimov is about to begin a safety test that will kill him, his crew, and thousands of others. But he doesn't know that yet. Right now, he's following orders. Orders that require him to disable safety systems. Orders that violate every protocol. Orders that assume nothing can go wrong. The test is simple. If the reactor loses power, will the spinning turbines generate enough electricity during their wind-down to power emergency systems until backup generators start? It's a reasonable question. It's been tried before at other reactors without incident, but those tests were conducted carefully with proper preparation, with all safety systems active. This test is different. This test requires disabling the emergency core cooling system, disabling automatic shutdown mechanisms, deliberately putting the reactor in an unstable configuration, and then seeing what happens. What happens is that at 1:23:40 a.m. on April 26th, Reactor 4 at Chernobyl explodes with the force of 400 Hiroshima bombs, releasing 400 times more radiation than the atomic bomb, creating a radioactive cloud that will contaminate half of Europe, turning 1,000 square miles into an exclusion zone that will remain uninhabitable for 20,000 years, and killing between 4,000 and 93,000 people, depending on whose numbers you believe. But in this moment, at 11 p.m. on April 25th, none of that has happened yet. The reactor is running, the operators are preparing, and they're about to make a series of decisions that will demonstrate something terrifying about human nature. When you combine arrogance, incompetence, institutional dysfunction, and a Soviet system that punishes bearers of bad news, you can turn a controllable situation into an apocalypse in less than a minute. Here's what most people don't understand about Chernobyl. It wasn't an accident. Accidents are unforeseen. Accidents are when something breaks unexpectedly. Chernobyl was deliberate choices, one after another, each compounding the previous error, each driven by the belief that Soviet engineering was perfect, that the reactor was safe, that nothing could go wrong. The operators disabled safety systems on purpose. They violated procedures intentionally. They ignored warning signs deliberately. And when the reactor started behaving abnormally, they didn't stop the test. They kept going because stopping would mean admitting failure. And admitting failure in the Soviet system could end your career or worse. Let me be absolutely clear about what happened. Chernobyl didn't explode because of equipment failure. It exploded because human beings, following orders from superiors who didn't understand the reactor's physics, disabled the safety systems designed to prevent exactly what happened, put the reactor in the most dangerous possible configuration, and then expressed surprise when physics did what physics always does: punish hubris with catastrophe. The operators who died in the first seconds, they're not the villains. They were following orders. They trusted their superiors who designed the test. They believed the reactor was safe because they'd been told Soviet RBMK reactors couldn't explode. They were wrong. But the wrongness wasn't malice. It was systemic. A system that valued political reliability over technical competence, that punished questioning authority, that insisted Soviet engineering was flawless, that created conditions where disasters were inevitable, and then blamed the workers when disasters occurred. By 1:24 a.m. on April 26th, the reactor core has melted through the floor. 2 workers are already dead, killed by the initial explosion. 30 more will die in the next 3 months from acute radiation syndrome. Thousands more will die over decades from cancers and other radiation-induced diseases. The Soviet government will deny the explosion for 48 hours while radiation spreads across Europe. They'll evacuate 350,000 people from contaminated areas. They'll send 600,000 liquidators, soldiers and workers, into the disaster zone to clean up radioactive debris, many receiving lethal radiation doses. They'll build a sarcophagus over the destroyed reactor using remote-controlled machinery because humans can't survive the radiation long enough to work near the reactor. The total cost? Impossible to calculate. Hundreds of billions in cleanup and containment. Thousands of square miles rendered uninhabitable. A generation of children exposed to radiation, causing thyroid cancers and birth defects. The final collapse of Soviet credibility. They couldn't hide this disaster, couldn't spin it, couldn't maintain the fiction that everything was under control. Chernobyl revealed Soviet incompetence to the world. 5 years later, the Soviet Union would collapse. Chernobyl didn't cause that collapse, but it contributed. It demonstrated that the system was broken at every level, from reactor design to operational procedures to governmental response. This isn't a story about nuclear power being dangerous, though it is if mismanaged. This is a story about what happens when institutional arrogance meets technical complexity, when political concerns override safety, when workers are trained to follow orders rather than think critically, when systems are designed by people who refuse to imagine worst-case scenarios because admitting vulnerability is ideologically unacceptable. Let me take you through that night, minute by minute, decision by decision, error by error. From 11 p.m. on April 25, when the test begins, through 1:23 a.m. on April 26, when the reactor explodes, to the days and weeks afterward, when the full catastrophe becomes undeniable, I'll show you how a safety test became a disaster, how every protocol violation made the next one easier, how warning signs were ignored or rationalized, how 43 seconds of exponential power increase destroyed a reactor that operators insisted was perfectly safe. And I'll show you why Chernobyl's lessons remain relevant. Because the same institutional dynamics, the arrogance, the refusal to admit uncertainty, the punishment of whistleblowers, the prioritization of political narratives over technical reality, these patterns exist in every complex system. Chernobyl happened in 1986 in the Soviet Union. But the conditions that enabled it exist anywhere humans build complex systems and then convince themselves those systems are foolproof. The reactor didn't fail. The people failed. And understanding exactly how and why they failed is the only way to prevent the next Chernobyl. To understand how Chernobyl happened, you need to understand the RBMK reactor design, Soviet institutional culture, and the specific sequence of decisions made on April 25-26, 1986. Each factor amplified the others, creating conditions where disaster was inevitable. The RBMK design flaw. The RBMK reactor had a fundamental physics problem called a positive void coefficient. In simple terms, if coolant boils and creates steam voids, reactivity increases, generating more heat, creating more steam, increasing reactivity further. A positive feedback loop. Most reactor designs have negative void coefficients. Steam voids decrease reactivity, creating inherent stability. The RBMK did the opposite. It became more reactive and unstable when coolant boiled. This wasn't secret. Soviet nuclear engineers knew about this characteristic, but they considered it manageable with proper procedures and safety systems. The reactor could be controlled as long as operators followed protocols and safety systems remained active. The RBMK also had another dangerous feature. At low power levels below 700 megawatts thermal, the reactor became unstable and difficult to control. Operations below this level were forbidden except during shutdown procedures. This was known. This was in the operating manual. This was taught during operator training. These design characteristics didn't make disaster inevitable. Properly operated, with all safety systems active and protocols followed, RBMK reactors were relatively safe. 15 RBMK reactors operated in the Soviet Union. Only one exploded. The design had vulnerabilities, but human decisions transformed vulnerabilities into catastrophe. The political context. The test being conducted wasn't new. It had been attempted 2 times previously in 1982 and 1984, but had failed to produce conclusive results. The test was scheduled for April 25, 1986, during a planned maintenance shutdown. Senior engineer Anatoly Dyatlov was in charge. He had authority from plant management. He had instructions about how to conduct the test, and he had political pressure to complete it successfully. Previous failures reflected poorly on the plant's technical staff. Soviet institutional culture created perverse incentives. Success was rewarded. Failure was punished. Questioning superiors was dangerous. Admitting inability to complete assigned tasks could end careers. This meant engineers and operators often concealed problems, minimized risks, and pushed forward with dangerous operations rather than admit they couldn't safely accomplish assigned objectives. Dyatlov personified this culture. He was technically competent but arrogant, dismissive of safety concerns, contemptuous of subordinates who expressed doubt. When operators raised concerns about test parameters violating safety protocols, Dyatlov overruled them. His attitude was that their job was to follow his instructions, not question them. The protocol violations begin. The test was supposed to begin in the afternoon of April 25th. Reactor 4 would be powered down from 3,200 megawatts thermal to 701,000 megawatts. The turbine test would be conducted, then the reactor would be shut down for maintenance. But at 2 p.m., the electrical grid controller in Kyiv requested that Chernobyl delay the power reduction. They needed the electricity. This was routine. The reactor stayed at full power. At 11 p.m., Kyiv finally allowed the shutdown to proceed, but this 9-hour delay meant the test would be conducted by the night shift instead of the more experienced day shift. The night shift had less experience with this reactor. They hadn't been briefed as thoroughly on the test. They were inheriting a complex operation mid-process. This wasn't their fault. Shift changes are inevitable, but it meant the most dangerous phase would be conducted by less experienced operators. Decision 1. Disabling emergency core cooling. To conduct the test, operators disabled the Emergency Core Cooling System, ECCS. The logic was that the ECCS would activate when reactor power dropped, interfering with test conditions. Disabling it seemed reasonable for a short test period, but this violated a cardinal rule: never disable emergency safety systems. If something went wrong, the primary protective system wouldn't be available. Akimov, the shift supervisor, was uncomfortable with this. He questioned whether it was safe. Dyatlov insisted. The test procedures approved by plant management specified disabling the ECCS. Akimov's choice was to follow orders or refuse and potentially face discipline. He followed orders. This decision didn't cause the disaster directly. The ECCS wouldn't have prevented what came next, but it established a pattern. Safety systems were negotiable if they interfered with operations. This mindset would govern all subsequent decisions. Decision 2. Losing control of power levels. As reactor power decreased, operators were supposed to stabilize at 700 to 1,000 megawatts. Instead, due to operational error, possibly a miscommunication between operators, power plummeted to 30 megawatts, far below the forbidden 700 megawatt threshold. At this power level, the reactor was unstable, filled with neutron-absorbing fission products, difficult to control. Proper procedure demanded shutdown. Once below 700 megawatts, operations shouldn't continue, but shutting down meant abandoning the test, wasting hours of preparation, failing to accomplish the assigned objective, and explaining to management why they couldn't complete a test that had been delayed already. Dyatlov ordered them to bring power back up, continue the test. This was the critical decision. Everything after this point was deterministic. At 30 megawatts, the reactor was poisoned with xenon-135, a neutron absorber that builds up during operation. Bringing power back up required withdrawing control rods to compensate for xenon poisoning. This would leave the reactor in a dangerous configuration. Decision 3. Withdrawing too many control rods. To raise power, operators withdrew control rods, neutron absorbers that regulate reactivity. They kept withdrawing rods until only 6 to 8 remained fully inserted in the core. The minimum safety requirement was 30 rods. They violated this by a factor of 4. Sensors alarmed. Computer systems warned that rod configuration was unsafe. Operators acknowledged the warnings and continued. Why? Because they couldn't raise power otherwise. Because xenon poisoning required massive rod withdrawal. Because they'd already committed to continuing the test. Because stopping now meant admitting they'd violated procedures by dropping below 700 megawatts in the first place. Each violation made the next one necessary to avoid admitting the previous one. By 1 a.m., operators had manually stabilized power around 200 megawatts, still below the safe threshold, still in unstable configuration, but enough to conduct the turbine test. The reactor was now in the most dangerous possible state. Low power, minimal control rod insertion, coolant flow reduced, multiple safety systems disabled, operating far outside design parameters. Normal procedure would abort, but aborting meant failure, and failure was unacceptable. Decision 4. Proceeding despite instability. At 1:22:30 a.m., operators began the actual test. They closed turbine steam valves, simulating loss of electrical power. The turbines began spinning down, and operators monitored whether they generated sufficient electricity to power safety systems until backup generators started. Closing steam valves had a side effect. With less steam leaving the reactor, coolant heating increased, generating more steam in the core. Remember the positive void coefficient? More steam meant more reactivity. Power began rising slowly. Operators noted this. It was expected. They could compensate by inserting control rods if necessary. But they'd withdrawn almost all the control rods already. Their ability to control reactivity was minimal. The reactor was balanced on a knife edge. Any perturbation could trigger runaway reaction, and they'd just perturbed it by changing coolant flow conditions. At 1:23:04 a.m., an operator noticed power rising faster than expected, not exponentially yet, just faster than calculations predicted. He verbally noted this to Akimov. They could still hit the emergency shutdown button, AZ-5, which would drop all control rods and shut down the reactor. This would ruin the test. It would mean failure, but it would be safe. Akimov hesitated. Dyatlov was watching. The test was almost complete, just 40 more seconds, and they'd have data. Power was rising, but not dangerously yet. They could finish. They were so close. They didn't hit AZ-5. Not yet. Decision 5, the 43 seconds. At 1:23:36 a.m., power was rising exponentially. Reactor control systems were losing their ability to compensate. Akimov ordered manual insertion of control rods. Operators complied, but rods moved slowly, taking 18-20 seconds to fully insert. And there weren't enough rods withdrawn to make much difference. They'd already inserted most available rods just to stabilize at 200 megawatts. 1:23:40 a.m., Akimov hit the AZ-5 emergency button. All control rods dropped. This should shut down the reactor. Instead, it exploded. Why? Because RBMK control rods had graphite tips. When first inserted, these graphite tips displaced water coolant, briefly increasing reactivity before the neutron-absorbing section reached the core. This was known as the positive scram effect. Hitting emergency shutdown briefly increased power before decreasing it. Under normal conditions, this was harmless, a brief power spike before shutdown. But the reactor wasn't in normal conditions. It was already in supercritical state, power rising exponentially. The positive scram effect added reactivity at exactly the wrong moment. Instead of shutting down, the reactor's power spiked to 33,000 megawatts thermal, 10 times normal operating power, in less than 3 seconds. 1:23:43 a.m., the fuel rods shattered, coolant instantly vaporized, steam pressure exceeded design limits. The reactor core exploded, lifting the 1,000-ton reactor lid, the Elena plate, and exposing the core to atmosphere. A second explosion, possibly hydrogen, possibly steam, blew apart the reactor building. Chunks of burning graphite and radioactive fuel scattered across the facility. The core was exposed, burning, releasing radiation directly into the night sky. Akimov and his operators didn't understand what happened. The control room instruments showed impossible readings. Too much damage, too many sensors destroyed. They thought it was equipment failure. They spent critical minutes trying to restore cooling, trying to save the reactor, believing it could still be controlled. They didn't realize the reactor no longer existed. It had been blown apart. There was nothing to save. They received lethal radiation doses in those minutes, trying to save a reactor that was already destroyed. Akimov died May 11, 1986, 15 days after the explosion, from acute radiation syndrome. His assistant, Leonid Toptonov, died May 14th. Both were 33 and 26 years old, respectively. They weren't incompetent. They followed orders. The system killed them. The explosion at 1:23:43 a.m. was just the beginning. The real catastrophe was what happened in the hours, days, and weeks afterward, a cascade of denial, incompetence, heroism, and tragedy that would contaminate half of Europe and create an exclusion zone that will remain dangerous for 20,000 years. The first minutes, denial. In the destroyed control room, operators couldn't comprehend what had happened. Their instruments showed conflicting readings. Radiation sensors were off-scale, showing maximum radiation levels, but operators assumed the sensors were damaged, not that radiation was actually that high. The reactor was clearly damaged, but surely the core was intact. Surely they could still cool it. Surely it wasn't as bad as it seemed. Deputy Chief Engineer Anatoly Dyatlov inspected the reactor hall from a doorway. He saw the destroyed building, the fires, the exposed core glowing in the darkness, but he couldn't accept it. An RBMK reactor couldn't explode. That was physically impossible. Therefore, what he was seeing must be something else. A hydrogen explosion, a steam explosion, something that damaged the building but left the core intact. This denial would persist for hours. Plant management, informed of the explosion, insisted the core was intact. They reported to Moscow that there had been a fire and an accident, but the reactor itself was undamaged. They ordered operators to resume cooling the reactor. They refused to believe physics had done what physics inevitably does when you put a reactor in supercritical configuration: destroy itself. The first hours: heroism and death. Firefighters arrived within minutes. They didn't understand what they were fighting. They saw a building fire, familiar, manageable with standard firefighting techniques. They climbed onto the roof of the turbine hall, directly exposed to chunks of radioactive graphite and fuel scattered by the explosion. They received lethal radiation doses within minutes. Many vomited from acute radiation sickness while still fighting the fire. All of the initial firefighters died within weeks. Shashanok, a worker in the turbine hall, was pinned by debris and burned. He received a radiation dose estimated at 2,000 rads, lethal. He was rescued but died hours later from radiation and burn injuries. Valery Kodamchuk was in the reactor hall when it exploded. His body was never recovered, entombed in the wreckage. He's one of 2 official immediate fatalities, though many more would die within weeks. Plant workers and engineers, ordered to restore cooling, entered highly radioactive areas without proper protection. They didn't know how dangerous it was. They'd been told the reactor was intact, that radiation wasn't that severe, that they needed to work quickly to prevent further damage. They obeyed. Many received doses that would kill them. The first day: the lie. April 26th morning. Soviet authorities in Moscow were informed of an accident but told the core was intact. Local authorities in Pripyat, the city built to house Chernobyl workers, population 49,000, located 3 kilometers from the reactor, were told there was no immediate danger. Normal life continued. Children went to school. People worked in gardens. A wedding was held. No evacuation was ordered. But radiation monitors throughout Europe were detecting elevated levels. Swedish monitors noticed increased radiation on April 27th. They initially thought it was from their own facilities, but determined it was atmospheric, carried by wind from the southeast. Other European countries confirmed the same readings. Something had happened in the Soviet Union. Something was releasing massive amounts of radiation. The Soviet government initially denied everything, but the evidence was undeniable. Radiation doesn't respect borders or propaganda. By April 28th, facing international pressure and mounting evidence, the Soviet government admitted an accident had occurred at Chernobyl, but they minimized it. A small accident, under control. No need for international concern. The evacuation: 36 hours too late. April 27th, 1:30 p.m., 36 hours after the explosion, authorities finally ordered evacuation of Pripyat. Residents were told to pack essentials for 3 days. They were reassured they'd return soon. They left everything: homes, possessions, pets, lives. They would never return. The evacuation should have happened immediately. Every hour of delay meant more radiation exposure, particularly for children, whose thyroid glands absorbed radioactive iodine-131. Thousands of children would develop thyroid cancer as a result of this delay. Many would die. This wasn't accidental delay. It was deliberate minimization of danger because evacuation would admit severity and cause panic. Eventually, 350,000 people were evacuated from a 30-kilometer exclusion zone, but wind patterns had distributed radiation irregularly. Some areas within the zone were relatively safe. Some areas outside the zone were heavily contaminated but not evacuated. The evacuation was based on geometric distance, not actual radiation measurements. This meant people in safe areas were displaced while people in contaminated areas remained. A failure of planning and measurement. The liquidators: 600,000 sacrifices. With the core exposed and burning, authorities faced a crisis. Radioactive smoke was releasing into atmosphere continuously. Fires in the reactor were consuming graphite moderator, spreading contamination. Something had to be done to contain the disaster. The solution was crude: bury it. Drop sand, clay, lead, and boron onto the burning core from helicopters. Smother the fire, entomb the reactor, build a barrier. This required flying helicopters directly over the exposed core, dropping payloads and flying away before crews received lethal doses. Pilots flew mission after mission, accumulating radiation with each flight. Many would die later from radiation-induced cancers. They knew the risks. They flew anyway because someone had to. But smothering the core wasn't enough. Radioactive debris was scattered across the facility. Hundreds of tons of graphite and fuel needed to be removed from roofs and grounds. This required human workers, liquidators, because radiation was too intense for remote equipment in many areas. Between 1986 and 1989, approximately 600,000 liquidators worked at Chernobyl. Many were soldiers, conscripted and given minimal protection. They worked in shifts measured in seconds or minutes, run onto a roof, shovel radioactive graphite over the edge, run back. Each shift earned a predetermined radiation dose. Once you reached your lifetime maximum, you were done. You went home and waited to see if you'd develop cancer. Many did. Estimates of liquidator deaths range from 4,000, official Soviet numbers, to over 60,000, independent analyses. Thousands more developed cancers, immune deficiencies, genetic damage that affected their children. They were heroes, sacrificing health and life to contain a disaster they didn't cause. The sarcophagus, entombing failure. By November 1986, a concrete and steel sarcophagus was built around Reactor 4, containing the radioactive ruins. Construction was rushed. Workers faced radiation exposure limits, forcing rapid construction with less precision than ideal. The structure wasn't designed to be permanent. It was emergency containment, meant to last perhaps 30 years. The sarcophagus did its job. It reduced radiation release dramatically. But it wasn't perfect. The structure developed cracks. Rain leaked in, creating radioactive water that had to be managed. The destroyed reactor inside continued to pose risks. Nuclear material could theoretically achieve criticality again if conditions changed. Monitoring and maintenance continued, staffed by workers who accepted radiation exposure as part of the job. In 2016, a new safe confinement structure was completed. A massive arch built away from the reactor then moved into position to completely enclose the old sarcophagus. This structure is designed to last 100 years and allow eventual dismantling of the reactor. But eventual is optimistic. The radioactivity inside will remain dangerous for millennia. Chernobyl isn't cleaned up. It's just contained temporarily. The human cost, impossible to calculate. How many people did Chernobyl kill? The answer depends on who's counting and what they're counting. Immediate deaths, 2 from explosion, approximately 30 from acute radiation syndrome in the first months. These are uncontroversial. Long-term deaths, this is where numbers diverge wildly. The UN estimates 4,000 eventual deaths from radiation-induced cancers among the most exposed populations. Other studies estimate 16,000. Some claim 60,000 or more. The variation comes from assumptions about low-dose radiation effects, which populations to include, and how to attribute cancers that developed decades later. The truth is probably in the middle. Thousands died. Tens of thousands were affected. Hundreds of thousands had their lives disrupted. Millions lived with fear of contamination. The cost is incalculable because you can't separate Chernobyl-caused cancers from background cancers with certainty decades after exposure. What's undeniable is the scale. An area the size of Switzerland was contaminated. 350,000 people displaced. A thriving city of 49,000 abandoned. Farmland rendered unusable. Forests killed by radiation. The red forest where trees turned orange and died. Wildlife killed, then, paradoxically, thriving in the absence of humans. The exclusion zone has become an accidental nature preserve, demonstrating that radiation is less harmful to wildlife than human development is. The disaster that should have been prevented. That would have been prevented if protocols had been followed, if safety systems hadn't been disabled, if operators had been empowered to say no to dangerous orders, if the Soviet system hadn't punished bearers of bad news and rewarded completion of objectives regardless of risks. Chernobyl was preventable. That's what makes it so tragic, and that's what makes its lessons so urgent. Chernobyl wasn't one person's fault. It was systemic failure at every level. Reactor design, operational procedures, institutional culture, governmental response. Understanding each failure point is essential to preventing future catastrophes. The design failure, RBMK hubris. The RBMK reactor was designed in the 1960s-70s. Soviet engineers knew about the positive void coefficient. They knew about instability at low power. They knew about the positive Scram effect. These weren't secret flaws discovered after Chernobyl. They were known characteristics that designers believed they could control through procedures and operator training. But this was hubris. Designing a reactor with inherent instabilities and relying on perfect human operation to maintain safety is bad design philosophy. Reactors should be inherently safe, designed so that physics itself prevents runaway reactions, even if operators make errors. Western reactor designs generally incorporated negative feedback mechanisms. The RBMK relied on active control to maintain stability. Why? Economics and politics. RBMK reactors were cheaper to build and could be constructed with Soviet technology. They also produced weapons-grade plutonium as a byproduct, serving dual civilian and military purposes. Safety was secondary to these considerations. After Chernobyl, remaining RBMK reactors were retrofitted with improved safety systems, but several continued operating into the 2000s. The last RBMK wasn't shut down until 2013. The Soviet Union built a reactor they knew was dangerous, operated it for decades, and decommissioned the last one 27 years after Chernobyl proved how dangerous they were. The operational failure, protocol violations, normalized. The test procedures for April 25-26 violated multiple safety protocols. These violations were approved by plant management. This approval normalized dangerous practices. If management says it's acceptable, operators assume it must be safe. But management didn't fully understand reactor physics. The engineer who designed the test, Anatoly Dyatlov, was competent but arrogant. He believed his understanding was sufficient. He dismissed concerns from subordinates as excessive caution. His confidence infected the system. If the senior engineer says it's safe, who are operators to question him? This created a culture where questioning authority was seen as weakness or disloyalty. Operators who expressed concerns were overruled or ignored. The institutional message was clear. Your job is to execute orders, not evaluate their safety. This is disastrous in complex systems where frontline workers often notice problems that distant managers miss. After Chernobyl, procedures were revised, training was enhanced, and officially questioning was encouraged. But changing culture is harder than changing procedures. The Soviet system fundamentally discouraged dissent. This culture contributed to Chernobyl and persisted long after. The institutional failure. Perverse incentives. Soviet institutions rewarded success and punished failure in ways that encouraged dangerous behavior. Completing objectives earned promotions. Missing targets earned consequences. This meant engineers and operators often concealed problems, minimized risks, and pushed forward with dangerous operations to avoid appearing incompetent. The test being conducted had failed twice before. This created pressure to succeed. Another failure would reflect poorly on the entire plant. When operations didn't go as planned, power dropping to 30 megawatts, proper response was to abort. But aborting meant failure. So operators continued, violating protocols to salvage the test. This pattern appears in every major industrial disaster. Challenger exploded because engineers were overruled by managers who faced schedule pressure. Deepwater Horizon exploded because safety concerns were dismissed by managers focused on costs. Chernobyl exploded because completing the test mattered more than following safety protocols. Fixing this requires changing incentives. Reward people who identify problems, not punish them. Celebrate canceled operations when risks are identified, not criticize failure to complete objectives. Make safety the primary metric, not productivity or schedule adherence. The Soviet system couldn't do this. Safety meant admitting vulnerability. Admitting vulnerability meant admitting Soviet technology wasn't perfect. That was ideologically unacceptable. So safety concerns were minimized, risks were concealed, and disasters were inevitable. The response failure, lies killed. The 36-hour delay in evacuating Pripyat killed people. Children who could have been evacuated immediately instead played outside for a day and a half, breathing contaminated air, absorbing radiation. Thousands developed thyroid cancer that could have been prevented by immediate evacuation or by distributing potassium iodide tablets to block radioactive iodine absorption. Why the delay? Because evacuation would admit severity. Because emptying a city creates panic and looks bad internationally. Because Soviet authorities valued appearance of control over actual protection of citizens. Because admitting a nuclear disaster meant admitting technological failure, meant admitting ideological failure. The initial denial was even worse, telling Moscow the core was intact, telling local authorities there was no danger, allowing normal life to continue while radiation spread. These lies were driven by the same logic. Never admit failure, never show weakness, maintain the fiction of Soviet competence regardless of reality. This pattern isn't unique to the Soviet Union. Governments regularly minimize disasters, conceal information, and prioritize optics over public safety. But the Soviet system made this pathological. Truth was whatever the party said it was, and contradicting the party line was dangerous even when the party line was demonstrably false. The solution is transparency. Release information immediately. Trust citizens with truth. Accept that disasters happen and that honest communication is more important than maintaining illusions of control. The Soviet Union couldn't do this. Modern governments struggle with it. But it's essential. Lies during disasters kill people. The universal lesson: complexity requires humility. Chernobyl's deepest lesson isn't about nuclear power specifically, it's about how humans manage complex systems generally. Complex systems fail, they fail in unexpected ways, they fail when multiple small errors compound, they fail when operators make reasonable decisions based on incomplete information, they fail when institutional pressures override safety concerns. Preventing catastrophes requires humility, accepting that complex systems are inherently dangerous, that we don't fully understand all failure modes, that operators will make mistakes, that designs will have flaws we didn't anticipate. This humility must inform every aspect of system design and operation. Design for failure. Assume operators will make errors and designs will have flaws. Build in redundancy, passive safety mechanisms, and graceful degradation. Make it hard to create dangerous configurations even if operators try. Empower frontline workers. Operators who directly interact with systems often notice problems that distant managers miss. Create culture and procedures that encourage speaking up, questioning orders, and stopping operations when something seems wrong. Punish concealment, not problems. Make hiding problems more dangerous to careers than revealing them. Reward people who identify risks, even if those risks delay projects or increase costs. Maintain healthy fear. Never assume systems are perfectly safe or fully understood. Treat complex systems with respect and caution. Question confidence. Investigate anomalies. Take warnings seriously. Chernobyl happened because Soviet nuclear industry had lost this fear. They believed RBMK reactors were safe. They believed their procedures were adequate. They believed nothing could go wrong, and that belief killed thousands. Reactor 4 at Chernobyl remains entombed in concrete and steel. The new safe confinement structure will contain it for perhaps a century, but eventually someone will have to actually dismantle the reactor, remove the destroyed fuel, and try to remediate a site that will remain dangerous for 20,000 years. This is Chernobyl's eternal cost. We created a problem that will outlast nations, ideologies, and perhaps civilization itself. The true legacy of Chernobyl is not the radiation, but the lesson in humility. The disaster was not a failure of technology, but a failure of human systems. It was a failure of a political system that valued the illusion of perfection over the reality of safety. It was a failure of an institutional culture that punished the bearer of bad news and rewarded arrogance. It was a failure of operators who were trained to follow orders rather than think critically. Chernobyl is the ultimate proof that physics does not negotiate. Yeah, you can lie to your superiors, you can lie to your citizens, you can lie to the world, but you cannot lie to the reactor core. When the operators violated every safety protocol, when they put the reactor in the most unstable configuration possible, they were not defying the Soviet system. They were defying the laws of nature. And the laws of nature responded with a force that shattered the reactor, the Soviet myth, and the lives of thousands. The long shadow, the human and environmental cost. Decades later, the immediate death toll of 31 people is a grotesque lie of omission. The long-term cost is a shadow that stretches across generations. The human cost. The official UN estimate of 4,000 eventual cancer deaths is widely disputed. Independent studies focusing on the 600,000 liquidators and the millions who lived in contaminated areas place the number far higher. Thousands of children developed thyroid cancer due to the delayed evacuation and lack of potassium iodide distribution. These were not abstract statistics. They were the faces of the system's failure. The liquidators, the true heroes of the disaster, returned home with a ticking clock inside them. Their lives shortened, their health destroyed, often forgotten by the state they saved. Their sacrifice was not just physical, it was a moral sacrifice forced by the arrogance of their leaders. The environmental paradox. The exclusion zone, a 2,600 square kilometer area, remains largely uninhabitable for humans, yet nature has reclaimed it. The red forest, where pine trees died from acute radiation, has been replaced by new growth. Wolves, boars, elk, and rare species thrive in the absence of human development. This paradox is a chilling lesson. Radiation is a powerful pollutant, but human activity, logging, farming, construction, is often a more destructive force on the ecosystem. Chernobyl created an accidental nature preserve, a testament to the resilience of life, and a stark indictment of our own impact. The question is not whether the environment can survive radiation, but whether it can survive us. The economic burden. The cost of the disaster is incalculable. Hundreds of billions of dollars were spent on the initial cleanup, the sarcophagus, and the new safe confinement, NSC. The NSC alone cost over $2 billion, a massive engineering feat funded by 45 nations. This is the price of containing a single moment of hubris. The economic cost continues today in monitoring, health care for victims, and the loss of productive land. It is a debt that will be paid by countless future generations. The global lesson. From Chernobyl to Fukushima, Chernobyl's lessons were not fully learned. 25 years later, the Fukushima Daiichi disaster in Japan demonstrated that even a technologically advanced, safety-conscious nation could fall victim to a similar systemic failure. Fukushima's failure. While triggered by a natural disaster, earthquake and tsunami, the core failure was institutional. Engineers had warned for years that the seawall was too low. Safety procedures were based on historical data, not on a true worst-case scenario. The culture of absolute safety in Japan's nuclear industry led to a complacency, a belief that it cannot happen here. This is the same arrogance that plagued the Soviet system. The failure was not the tsunami, it was the failure to imagine the unimaginable, the universal pattern. Both Chernobyl and Fukushima reveal the same three systemic flaws that exist in every complex, high-risk industry. 1. Normalization of deviance. Small protocol violations become routine until a major one triggers disaster. 2. Failure of imagination. The inability to conceive of a true worst-case scenario. 3. Institutional arrogance. The belief that the system is foolproof and that safety is secondary to production or political goals. The final psychological trap, the arrogance of control. Chernobyl's deepest psychological lesson is about the illusion of control. The Soviet engineers believed they could control the RBMK reactor, a machine with inherent instabilities. They believed they could disable the safety systems for a test and bring it back under control. They believed their will and their ideology were stronger than the laws of physics. This arrogance is the ultimate human flaw when dealing with complex systems. We build machines of immense power, nuclear reactors, global financial markets, artificial intelligence, and then we convince ourselves that our procedures, our regulations, and our intelligence are sufficient to contain them. We forget that every complex system is a black box with hidden failure modes. The operators who died in the first seconds were not villains. They were victims of a system that taught them to fear failure more than they feared catastrophe. They were trained to follow orders, not to question the fundamental safety of the system. The only way to prevent the next Chernobyl is to cultivate the humility that the Soviet system lacked. It means designing systems that are inherently safe, not just procedurally safe. It means empowering the frontline worker to stop the process when something feels wrong. It means rewarding the person who raises the alarm, not the one who maintains the illusion of control. The unspoken question. The reactor is contained, the radiation is slowly decaying, but the arrogance that caused the explosion is still out there. Remember Chernobyl. Remember the cost of believing that your system is foolproof. Remember the price of silencing the voice that says, "Stop, this is wrong." Because the next time arrogance meets physics, the consequences will be just as absolute. The final, terrifying question Chernobyl forces us to ask is this: where are we disabling the safety systems in our own complex world? Are we disabling the ECCS in our financial markets, believing that deregulation and complexity will never lead to a meltdown? Are we withdrawing the control rods in our climate, believing that the laws of atmospheric physics will somehow bend to our economic needs? Are we ignoring the alarms in our political systems, believing that the arrogance and denial that plagued the Soviet Union cannot happen here? The pattern repeats because the human mind, when given power, will always prefer the illusion of control to the devastating truth of its own fallibility. The question is not if the next catastrophe will happen. The question is which safety system will be disabled next, and who will be the one to finally hit the AZ5 button when it's already too late.